Hi, good morning. So I hope I'm audible and the screen is visible. So today we are going to look at graphs. Okay. So graph is a very important in terms of its application because it has a wide variety of applications and there are many types of graphs and there are many algorithms related to it. So you will study more detailed algorithms where graph its applications in another course algorithm design. But here, since we are dealing with other data structures, we need to also, so far we have looked at more linear data structures like stacked linked list, queues, and then we looked at some non-linear data structures like trees. Now graph is I would say a superset of tree data, nonlinear data structure, where tree is also a graph data structure. Okay, so when you have a list of nodes and you have a way to express the relationship between nodes, that is what is a graph. And tree is also a graph, but not we can say tree is also a graph, but every graph is not a tree. So that is how it is. So we will look at an overview of graph. And in this course, we will not get into much details on the applications of graph algorithms. So there are many shortest path algorithm, there are minimum spanning tree algorithms, cycle detection algorithms. There are many such algorithms. But what here we will look at here is what is a graph? What is a node? How do you represent relationship between nodes in a graph? What is a vertex edge? How do you represent them? And most importantly, how do you structure them? And plus, how do you traverse through them? Breadth first and depth first. So these are how the traversals, like we had three traversals. In order, post order, pre order. We will look at two types of traversals in a graph alone in this course. So that is what I intend to cover this next in this session and in the next session. Okay. Any questions before I begin?
No, ma'am, all good.
Okay. Okay. So what exactly is a graph? Now we have a node. Okay. For example, say I, I'm having a airport reservation system. Okay. And I want to uh, say I'm running my services in 3 cities, or say, let's say 4 cities. So each of these cities, say I take Chennai, Delhi, Hyderabad, and let's take Bangalore. So these are the 4 cities I'm running my services. Do I have connectivity from Chennai to Delhi? Then this is how I represent. Do I have a connectivity from, say I have a air service running from Chennai to Delhi and Chennai to Hyderabad. Okay, but I don't run a air service from Chennai to Bangalore. Okay, so this is how it is, right? Now, when I have a arrow mark like this, it means that Chennai to Hyderabad I have a service, but this arrow mark clearly doesn't say that Hyderabad to Chennai there is a service or not. Okay, so when you have an arrow mark in one direction, it is a single direction. Okay, it's a directed graph. Okay, so when you have an arrow mark, either this, whatever it is, so this is a directed graph. So this picture means you have a flight running from Chennai to Hyderabad. You have a flight running from Delhi to Chennai. But what about Hyderabad to Chennai? Or what about Chennai to Delhi? That's a question mark. We don't have any information from this particular graph. So only if you have another vertex indicating that it is true. Okay, so this is in a directed graph. But generally, when you have, say, you have a line, say I just draw a line like this between D to H, okay, without any arrows, that's an undirected graph. It means that you have a path from D to H as well as H to D. So if it's there is no direction in an undirected graph, it means that both Delhi and Hyderabad are connected. So now let's look at the nomenclature. So all these nodes are the vertices. So a graph has a set of vertices and a set of edges. The set of edges are the ones which connect the vertices. And an edge is represented as E, U, comma, V pair. So U is the source, V is the destination. So edge is always represented by a pair of vertices. So if you look at this particular example, we have 5 nodes. They are the vertices. So the vertex set has A, B, C, D, and E. The edges are A to B, A to C, A to D, and B to E, B to A. Sorry, B to E and C to D, C to E, and D to E. Okay. Now, when I say A to B, since this is a directed graph, B to A is also correct. Okay. So, I mean, it's an undirected graph. There is no indication. So, B to A is also there. Okay. So, these are the set of vertices. Now, if you look, this is an example of a flight route between different. Now, if you see the vertex represents the airport and it stores a 3-letter airport code. Okay. And the edge represents the flight route between the two airports and it shows the mileage of the route, how much distance it takes. Okay, so this is a representation of a graph. So another very common real life example of a graph is our connections in social networks and other places. So for example, say we have a set of 6 people, John, Mary, Joe, Helen, Tom, and Paul, and each of them of age different, right? So you can see the vertices are of these people, right? And edge x comma y, there will be an edge if x is younger than y. Okay, so if x is younger than y means, for example, let's take John. Okay, John is 12. So wherever you have John as the younger part, you will have a edge. So you can see John is younger than Mary, right? Then Joe, and Helen. Not Helen, right? Mary, Joe, Helen, Tom, and Paul. Okay, Helen is equal. Okay, so from John, you can see you have a H to Mary, you have a H to Helen. Okay, you don't have, oh, sorry, Helen is 15, Joe is equal. So you don't have a H to Joe, you have a H to Helen, you have a H to Paul, and you have a H to Tom. Okay, so if you take Mary, 15, right? It is the highest. So you don't have any edge going from Mary at all because Mary is not younger than anyone. So you don't have an outgoing edge at all from Mary. Okay. So similarly, if you take Joe, who's 12, it will be same as John. Okay. So you'll have a path to Helen, you'll have a path to Mary, Tom, and Paul, but you'll not have a edge to John. Okay. So from Helen also, you will not have any outgoing because it's the largest. From Tom, you will have only to Mary and Helen, and from Paul also you'll have Mary to Helen. So this is one example of a graph. Now, where is this graph useful? as I mentioned, any network you want or any relate, you have a set of nodes and you want to express the relationship between the nodes. That is where graphs are used, and they are useful in many places, the graph algorithms. So in printed circuit boards, integrated circuits, networks, and all local area computer networks, graph algorithms are used. So shortest path. So if a packet has to go from network path has to go from this layer to this, again, it has to pass through this, right? Which is the shortest path, which it will travel fast, which is the less congestion path. All that algorithms are useful through the graph-based algorithms are there. Entity relationship diagram. So when you study database, you will understand how the entity and the relationship are mentioned. So that is where you will have a good understanding of the different requirements of a graph, right? So all these places graphs have been quite useful in real time. Now let's look at some of the nomenclature. Now, as I told you earlier, the edge can have directions. It can indicate that whether it is from one place to the other or it is undirected. That is, it is mapping to the both the sides, right? So if it's a directed edge, it will have an arrow. So which means that the first vertex is U and the second vertex, the destination, or the origin is U, destination is V. So this for any flights or any direction based communication, you use a directed edge. When you say you don't have any arrow, it is an undirected edge. So it is an unordered pair of vertices. So you say UV. Even if you say V comma U, it is the same as UV. Okay. So flight route, if both directions are available, you just say that it can be mentioned as an undirected edge. So when all edges are directed, like with an arrow pointing, then you call that graph as a directed graph or digraph. When all edges are undirected, as in a route network, you can say that graph as an undirected. And some more terms which we have to understand. Okay. So if a node, say in a graph, okay, in a graph, you have a vertex V0, V1, V2, V3 like this. If a node has a direct edge connecting each of the vertices, okay. So if you say if V0 and V1 are adjacent, which means that the edge is incident on the vertices V0 and V1. Okay. So you have an edge directly connecting between two vertices. Then those vertices are called as adjacent vertices. If V0, V1 is an edge in a directed graph, V0 is adjacent to V1, but V1 is not adjacent to V0. So how do you have to picture this is, okay, let's say, let's take our flight example because that's more applicable. So let's say I have Chennai, I have Delhi, I have Hyderabad and Bangalore. Okay. Now I have a connection from Chennai to Delhi. I have a connection from Chennai to Hyderabad. And I have a connection from Hyderabad to Delhi. And I also have a connection from Bangalore to Hyderabad. Okay. Okay, so say this is my graph. Okay, now C comma D, are they adjacent nodes? Whether C and D are adjacent, right? C is adjacent to D, okay? Because you have a direct edge. You have an edge C comma D where it starts, the edge is incident on the vertices V0 and V1. Okay, you have a edge which is starting in C and ending in D. So C is adjacent to D. Okay. Similarly, D is adjacent from C. Okay, D is adjacent from C, not to. Only if you have an edge in this direction, D is adjacent to V, so it is from, it is not to. Okay, C is adjacent to D. D is adjacent from C. Okay, why? Because you can go from Chennai to Delhi in one hop. They are adjacent. But from Delhi, you have to go, you don't have a direct path to uh, through Delhi. Okay, so that is how it is. Okay, so the edge is incident on V0 and V1. So in a directed graph, that is more important. So you have to see whether they are adjacent, means they should have a direct path between each other. Okay. In undirected graph, it is not at all a problem because they are directly connected with each other. So the degree of a vertex is the number of edges incident to that vertex. So for for a directed graph, right, you have two things, in degree and out degree, right? So here, if you just see a normal graph, okay, 1, 2, 3, 4, number of edges is calculated. So number of edges incident on that vertex. In a directed graph, there is an in degree, which is the number of edges that are starting, that have V as the head starting point. Out degree is the number of edges which have a tail at, that is reaching this. Okay, so you have to calculate the in degree and the out degree separately, and the total degree is in degree plus out degree. So the degree of a vertex in a graph is, with n vertices and e edges, is the number of total edges. So all the edges, if you calculate the sum, it will be the total number of edges by 2. Okay, I will tell you why by 2. Say this example, G1. Okay, what is the degree of 1? 1, this is 1, 2, and 3. So 3 is the degree. 0, if you take, it is 1, 2, and 3. The number of edges is 3, so the degree of 0 is 3. The degree of 2 is also 1, 2, and 3. The degree of 3 is also 1, 2, and 3. Okay. Now, what about degree of G2? 0 has 2 edges. So the degree of 0 is 2. The degree of 1 is 1, 2, 3. So 3 edges are going from 1. So it is 3. The degree of 2 is also 3. The degree of 3, 4, 5, and 6 is 1 each. Okay. Now both these are undirected graphs. So degree will be counted twice. Okay. So if you add all, if you take a summation of all the degrees of all the nodes, that is, in this case, you say 3 plus 3 plus 3 plus 3. Okay. If you take the summation of all this, you get 12. Okay. So if you do a 12 by 2, you get 6. 6 is the number of edges. Why you are getting 12 is every time it is counted twice. For example, if you take this particular edge, in 1 also it is counted once, and in 0 also it is counted once. So it is counted twice every time. That is why the total degree of all the vertices. If you sum it, you will get number of edges into 2. So that is number of edges is by 2. So it is counted here as well as counted here. In case of a undirected graph, this is applicable. In case of a directed graph, it has one out and one in. This in has 2 outgoing. So you see outgoing nodes, out degree is 2 and incoming is 1. And if you take 2, it has only 1 incoming, there is no outgoing. Okay. So if you take the in degree of, it is number of incoming, out degree is number of outgoing. Okay. So even if you sum the total degree, if you take, so this is 2, this is 3, this is 1. Okay. So if you add, it is 6. Okay. And this is by 2. So if you take the total degree here, again, the number of edges, if you take all the degree of a vertex in a graph with the n vertices and summate that, it will be number of edges by 2. Okay. So this is applicable for directed graph also. Any questions till now? Is it clear?
Ma'am, if there are seven edges, then what if it comes decimal, if we divide by 2?
Mostly it will not be decimal.
Okay.
Say this is our graph. Okay. I will. So what is the degree of A, B and C? A will be 2, B will be 2. This also will be 2.
2.
Okay. So edge is counted, right? So it will not become decimal. Every edge is counted twice. So you will get mostly an even number only. Okay, let's take a graph like this. Okay. Tell me what is the degree of A? 3, right? B is 2.
2, 3.
3. 3. This is 3. Correct? So
Yes.
3 plus
14.
3, 6, 12, 14 by 2, 7. So 1,
Okay.
2, 3, 4, 5, 6, 7. 7 edges are
Okay.
there.
Yes.
So any graph you see, it will almost be same only. So maybe we will do for this this graph also. What is the degree of John? 1, 2, 3, 4.
4.
Mary 0. Mary 0.
0.
Plus 4. In degree is 0. Sorry, in degree is 4, out degree is 0. So it is 0 plus 4. So Tom also 2 in degree, 2 out degree. So 4. Paul 1, 2, 3, 4 in degree 2, 4. This is 1, 2, 3, 4. This is
4.
also 4, right? So
Yes.
1, 2, 3, 4, 5, 6, 24.
24. Yes.
12. So we will have 12. 1, 2, 3,
3, 4, 5,
6.
yes. 12.
Okay. So
Yes.
12. So that's how you will get it. Now we will look at some more terminology. Okay. So still now we have saw what is a vertex, what is a edge, what is a degree, what is in degree, out degree, directed graph, out in undirected graph. Okay. Now what is a path? Okay. In a graph, if you go through a sequence of alternative vertices and edges, you begin with the vertex and ends with the vertex, different vertex. Each edge you follow, that is a path. And in this, all the vertices and edges are, if all the vertices and edges are distinct, that's called as a simple path. Okay, if it's not distinct, it is a normal path. Okay, so you have, say for example, you start from U and you go to V. So how you can go from U and go to V? You can just go U. You have to write a sequence of vertices plus edges. Okay, so you start from U, you go to A, and then you reach V. This is one path. This path is also simple path because the edge and the vertices are distinct. Okay. Now from U to go to U to V, there is another path. I start from U, I go to CH, then I go to W. From W, I go to FH, then I go to Y. From Y, I go to G, then I go to X. Okay. From X, I go to say B, and then I reach V. So this is also a path between U to V. So this is a path, right? Is this a simple path or not? Are there any repetition? If I go U, V, Y, X, V, am I repeating any path? No. So this is also a simple path. Okay. So remember, these are all simple paths, but these are not the shortest path. So this may be the shortest path. Okay, we are not talking about shortest path here. Okay, this is a path. This is also a path. Both are simple path because we don't have a repetition. But consider this path. You start from U, you go to C, you go to W. From W, you go to E, you go to X. Then from X, you go to G, you go to Y. From Y, you go to F, W, D, and then you reach V. Okay. This is also a valid path, but this is not simple path. Why it is not simple path? Because you go through this W path, right? Vertices, you repeat it. The vertices and edges are not distinct. So it is not a simple path. So you have a path to connect two vertices. It starts with the vertex and ends with the vertex. Each edge is preceded and followed by its endpoints. If all the vertices and edges are distinct, it is a simple path. If it is not distinct, then it is a normal path. Okay. Now if you start the path, whichever you saw here, if it starts with the same vertex and ends with the same vertex, then it is a cycle. Okay. You start with the individual vertex. You go through different edges and vertices and you reach the same destination. That is a cycle. And again, the same like a path. If all the vertices and edges you have traveled is distinct, right? It is a simple cycle. Otherwise, it's just a cycle. Okay, you have to go through each of this. So in this example, you start from B, you go to B, then you go to X, then G, Y, F, W, C, U, A, and you reach the source itself. It is a simple cycle because there is no repetition. Okay. Now this C2 is also a cycle because you start from U, you go to C, you start from U, you go to C, W, then you go to EX, then you go to G, then you go to Y, F, W, then you go to D, B, and then you reach E. So you start with U, end with U, but you have repetitions. You have W repeating. So this is not a simple cycle. It is still a cycle, but it is not a simple cycle. So I hope you understood the difference between path and cycle, simple cycle and simple path. Okay. Path is a path between any two vertices. A cycle is you start with the same vertex and end at the same vertex. In a simple cycle or a simple path, the vertices and edges have to be distinct. Now coming to the properties. This is a proof of that. So I told you if you take a summation of all the degrees, you will get 2 into number of the edges because each edge is counted twice. Okay. In a undirected graph with no self loop and no multiple edges, okay, it's a fully connected graph. You will have a vertex at degree at most n minus 1. Okay, I will tell you this. So n is the number of vertices. Okay, so here what is n? Equal to 4. M is the number of edges. What is the number of edges? 1, 2, 3, 4, 5, 6. Okay, and what is the degree? 3, 3, 3, 3. Right? So the summation of degree is 12, which is equal to 2m. So this, I think you don't have a problem. Right? Now, if it is a well-connected graph, okay, it's a complete, that is, it has connectivity to all the edges. Maximum in a undirected graph, okay, maximum how many edges a node can have? So how many maximum edges this node can have? 3 only, right? Because only 3 nodes are there. So it can have
Yes,
only
ma'am.
three edges, right? There are no, we don't consider self loop. What is a self loop is if you have a edge like this, okay, that is a self loop, but we don't consider self loop or no multiple edges. So sometimes multiple edges are also possible. We don't have a requirement in this. It depends on the application. I will tell you when multiple edges will be possible. For example, take our telephone connection, okay? We will have one connection between this computer to this computer, which has maybe 1 Mbps speed. And then we might have another connection with 10 Mbps speed. Okay, so that in those scenarios, multiple edges will be required. Okay, but let's take an undirected graph with no self loops and no multiple edges. Okay, the maximum number of edges this can have is 3. Okay, and this can have is 3, this can have is 3, this can have is 3. So in an undirected graph, the maximum number of edges a vertex can have is n minus 1. Okay, so if there are n edges, sorry, n vertices, the maximum edges I can have is n minus 1. Say you are a group of friends of 4 people. Now you have you have to talk to each of them. How many calls you have to make? 3 calls, right? So the maximum number of edges each node will have always is n minus 1. If you are a group of 6 people, you have to talk to each of them. How many calls you have to make? 5 calls to talk to each of them, right? So each vertex will always have at most n minus 1. So if each vertex is having at most n minus 1 graph, so this is n minus 1, this is n minus 1, this is n minus 1, this is n minus 1. So the total number of edges will be n into n minus 1, okay, which will be equal to twice the number of edges. So why? Because the edge will be counted here also twice, okay. So that is what this formula represents. M, the number of edges, will be equal to n into n minus 1. So 2m, right? So you bring that here by 2. Okay, the number of edges will always be this, but it will not always be equal to this, because sometimes you might not have this edge also. It is not, not a well connected graph, right? So the same graph, same graph I can have uh, like this also. So in this case, what is m is equal to 4 only. N is equal to 4. So this is not a complete connected graph, but this still is applicable. So that is why we say m will be less than or equal to n into n minus 1 by 2. Okay, it can be anything within n into n minus 1 by 2, but it will not be more than n into n minus 1 by 2. So it will not be more than 12 in this case. In an undirected graph, it can be only, sorry, 6 twice. Yeah, so that is n is 4, right? 4 into 3, 12 by 2. So maximum number of edges will be 6, but it can be m is equal to 0, 1, 2, 3, 4, 5, or 6. But it will never be 7 or 8 or 9 in an undirected graph. So that is why we say less than or equal to. Okay. So this is one property. Any doubts in this degree? All
No,
right,
ma'am.
I'll go. Okay, fine. Next, we will look at some more terminology. What are the other types of graphs? If any two vertices are connected by some path, we call this as connected graph, because it's all the vertices are connected with each other. So it's a connected graph. This is also a graph, but there is no connectivity between these nodes. So it's a not connected graph, but it is still a connected graph only. Okay. So connected graph means well-established connectivity is there. And a subgraph is a subset of vertices and edges forming a graph. So if you take this particular graph, this path, this is a subgraph, or this is a subgraph. Okay. A subgraph is a subset of vertices and edges forming a graph. That is a subgraph. And maximum connected subgraphs is the graph below has 3 connected components. This entire thing is treated as graph. Okay. But you don't have a connectivity from this to this, or you don't have a connectivity from this to this. So if you add a connectivity, it is a complete, you say it is a connected graph. But since these connections are not there, you can see the number of connected components is 3. So number of connected components is where all the verticals are connected to each other. So when you say connected component, what I'm meaning is, can I reach from this place to the other place? Can I connect? Now, say if I'm starting at this position, I can go here, here only, right? I cannot go to this node or this node. So that is why the connection is not there. So that's why it's called as a non-connected graph. So let's look at subgraph. So if you take G1 as an example, 0 alone is a subgraph. 0, 1, 2, this part of it is a subgraph. This is a subgraph. This is also a subgraph of G1. So all these are subgraphs of G1. Similarly, if you take this graph G3, this is a subgraph. Only 0 to 1, this is a subgraph. This is also a subgraph. This is also a subgraph. This is also a subgraph. Okay. So this is a subgraph of G3. So subgraph is a subset of vertices and edges. Now, what is a tree? It is also a graph, as I told you, but it is a special case. In tree, each node can have 0 or more children. A tree is a acyclic graph. Okay. So what is an acyclic graph? It doesn't have a cycle. So in this graph, you have a cycle. You can go from 0 to 1, and so In this graph, you have a cycle. You start from 0, if 3, you go and you can reach 0. So that is a cycle, right? I told you what is a cycle. If a graph does not have a cycle, right, that is called as an acyclic graph. And a tree is always a acyclic graph. So if you take a tree, it is never a, so this is a graph only, right? But it is never a cyclic. So you cannot have a cycle in a tree. So that is why it is an acyclic graph, right? And forest is a collection of trees. So you have multiple trees, okay? Like say I have one node like this, then I have another like this. Say I have some connected components, each of this like this. All together they form a graph, which is called as a forest. Okay. Now let's look at how to represent graphs in a program. Okay, now you know graphs, what is vertices, what is graph, what is cycle, what is path, what is the degree, all that you know. Now, how do you write program? How do you represent graph in the program? Right? How do you represent a stack? You can use a array, int array of 5 and you create, or you create a linked list. So you create a node which can hold, you can create a structure for a tree. So you have, for a tree, if you say you have a node, you create a node, then you have an integer data, then you create a left pointer, then you create a right pointer, right? So this is a struct. So that's how you represent a tree, right? So if the left points to a child, that's the left child. If this points to a child, this is the right child. So you represent that. So how do you represent a graph? So adjacency matrix and adjacency list. Okay. So now how do we first look at adjacency matrix and then we will go to adjacency list. So let graph is equal to vertices of V is the number of vertices, E is the edges. Okay. The adjacency matrix is a two-dimensional array, n by n array, where n represents the number of vertices. Okay. And if there is an edge exist from one vertex vi to another vertex j, then the value of that matrix will be 1. Value of that particular cell in that particular matrix I comma j will be 1. If there is no edge, then it becomes 0. So the adjacency of an undirected graph will be symmetric. So what is a symmetric matrix? Do you know? You would have learned linear algebra, right? So what is a symmetric matrix? The upper triangle will also be equal to the lower triangle of the matrix, right? So in this case, right? So here let's look at how to write an adjacency matrix. Say this is 0, this is 1, 2, and 3. So 0, 1, 2, 3. So the number of vertices is 4. So this is a 4 cross 4 matrix. Okay. So now 0 to 0, there is no self loop. So it is 0. 0 to 1, there is a path. So you add 1. 0 to 2, there is a path. You add 1. 0 to 3, there is a path. You add 1. Again, 1 to 0, there is a path. 1 to 1, it is 0. 1 to 2 is 0, 1. 1 to 3 is 1. 2 to 0, there is a path. 3 to 0, there is a path. 2 to 1, 3 to 1, there is a path. 2 to 2, there is no self loop, so it is 0. 3 to 3, there is no self loop, it is 0. Now, if you look at this matrix, the upper triangle, the in is same, right? So this is a symmetric matrix. If you look at a directed graph, okay, say 0. So this is 0, this is 1, this is 2. 0 to 0 is 0. 0 to 1, there is a path, so you add 1. 0 to 2, there is no path, so it is 0. And 1 to 0, there is a path. 1 to 1, there is no path. 1 to 2, there is a path, so you add 1. From 2, there is no outgoing, so it is all 0. Okay, now if you look, this matrix is not symmetrical, right? It is not symmetric matrix because it's an undirected graph. Sorry, it is a directed graph. Only in an undirected graph, the adjacency matrix of an undirected graph is symmetric. In the directed graph, it need not be symmetric. It can be symmetric. There is no restriction, but it mandatorily, it need not be symmetric. That is for an undirected graph. And if you take this G4, okay, so say this is 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. So this is the 8 cross 8 matrix because the number of edges is, sorry, vertices is 8. So it's an 8 cross 8 matrix. So from 0, you see, you have a path to 1, 2, and 3. So this also should, you don't have a path from 1 to 3. So you have only one here. So if you look, this matrix is also symmetric. Okay, because it's an undirected graph. Okay, so for this, let's see how to write the adjacency matrix. So how many vertices are there? 7 vertices are there. So it is a 7 cross 7 matrix, right? So from 1, you will see 2, 5, and 7. 2, 5, and 7, you have, 2, 5, and 6, you have 1. From 2, 1, 7, and 3. So 1, 7, and 3, you have 1. Others are 0. From 3, only 3, 2 and 4. So 2 and 4 you have. And from 5, you have 1, 7, 4. So you have 1, 7, and 4. And 6 also, sorry. So like that, you write the adjacency matrix. Now from the adjacency matrix, to determine the connection of vertices, it is very easy. Okay, so the degree of vertices is the summation of all the I plus j if you take. Okay, so if you want to find what is the degree of 2, it is 3, right? So if you add these summation of all this say adjacency matrix of I comma j of that particular row alone. Okay, so this will be 2 comma j, where j will be from 0 to n. Okay, if you add all this, you will get the degree of 2. Okay, so the degree of a vertex can just be calculated by summation of running that for the entire row. Okay, for a digraph, this row sum is the out degree, while the columns sum is in degree. Now, what is the problem with this adjacency matrix is to store 7 vertices and edges, you have to have a 7 cross 7 matrix. Okay, so 7 cross 7 matrices means n squared is the number of memory cells it requires. Even if you have a very sparse matrix, when I say sparse matrix, the number of connectivity is very less. Okay, say I have some 8 nodes. Okay, but say I have very few edges like this. Okay, to just store 3 edges, I have to use a 8 cross 8, 64 memory, 64 cells of memory. Okay, no matter how few edges are there, always you have an order of n squared as the matrix, which is the disadvantage of storing the data in an adjacency matrix. If it's a well-connected matrix like this, G1, it is not a problem. But if it is a sparsely connected matrix like this, right, you have many cells which are empty, which will not be used at all. So that is the problem with an adjacency matrix. Okay. Next, we will have to see adjacency list. Okay. Let's take a quick break here for 10 minutes. We will come and see adjacency list. So let's continue. So we will look at adjacency list representation. So in the adjacency matrix, the problem is you have to have a lot of memory. But in adjacency list, what we do, we use a linked list. Okay, so we create a representation based on the number of vertices. So if there are, say, 4 vertices, we create an array of 4, size 4. Okay. And then we maintain a linked list pointing to each of this like a hash table. So Li is the linked list which maintains all the nodes, all the edges which are of 0. That 1 is the linked list which maintains all the edges which are of the node 1, like that. So Li is the linked list containing all the nodes adjacent from that particular node. So this way you are able to use only the number of edges which is required. So in this example, if you see, so I have a 0. It's connected to node 1, 2, and 3. So I have 1, 2, and 3 here mentioned. From node 1, it is connected to 0, 2, and 3. So like that, I maintain a linked list. Same for undirected graph. If you look at this, so how many memory space? It's again, if it's a fully connected graph, almost 4 into 4, 16 memory is required here. And the same is required in this also, right? That's what we require. So if it's a fully connected graph, adjacency matrix itself is sufficient because that's easy to manage. But if it is like a sparsely connected graph, you can see if this, we will use 3 cross 3, 9 is the memory space, but here you'll see we have used only 6 of it. So, and an undirected graph, you just need a few. If it's a graph with very less edges, in the adjacency list is a more useful representation, whereas adjacency matrix is a more easier representation, but it has a lot of wastage of space. So for the same graph which we saw an adjacency matrix, here is the adjacency list example. So you take 1 and you say you have it is connected to 2, 5, and 6. So you see 2, 5, and 6. Like that, you maintain a separate linked list. Now, what is the advantage of adjacency list? It saves on memory space. It is only whatever edges are present, that only you will have use the memory. But what is the problem here? To identify whether a node is connected to another node. Okay, say you want to find in an algorithm, there is a requirement whether you want to check whether there is a direct edge between two nodes. Okay, say I want to check whether 2 is connected to 5 directly. Okay, in an adjacency matrix, how do I do this? So I want to check 2 is connected to 5 means I just go and see read A of adjacency matrix of 2, 5. That's all. So I go 2, 5, I see 0. I will say immediately it is not connected. So I will read that in one order of 1 time itself in an adjacency matrix. But in an adjacency list, what happens? If I have to say 2 is connected to 5, I have to start with 2, then traverse through this, see whether 5 is present or not. So I have to traverse through the linked list. And since I have to traverse through the linked list, what will be the maximum length of the linked list? This linked list, one linked list, what is the maximum length? It will be n minus 1 because the maximum number of edges a particular vertex can have is n minus 1 that we already saw, right? If there are n vertices, the maximum number of edges in one vertex is n minus 1, right? So if you take 7, it can have maximum n length if it is connected to all nodes. So in worst case, if it is present last, or if there is no edge present between 2 to 5, I have to traverse through the entire list. So to find out whether 2 nodes are connected, it will take order of n time for me. Okay. So one would have to search the entire linked list, which takes proportional time to the length of the Li, which is one of the disadvantage. So in an adjacency matrix, it is easier to tell whether an edge exists between two vertices I and j, but disadvantage it consumes a lot of memory on a sparse graph, and it has redundant information because the symmetric matrix upper triangle and the lower triangle are same. It has a redundant information. Okay. So now this is the graph ADT. The vertices and edges are there. Okay. These are the positions. They store the elements. So what are the methods which are available and what are the ADTs which are possible? Okay. So vertex represents all the vertices. Incident edges, it's the source. End vertices is the edges, if it is directed or not. What is the origin, destination? Opposite of V comma E is E starts from V, but it ends in one node, right? So when you say opposite of V comma E, you'll get where it ends. That particular edge where is the other end, the tail end of that edge that is given, and checks whether two nodes are adjacent or not. So number of vertices, number of edges, vertices, the list of vertices, list of edges. Do you want to insert an edge vertex, insert a directed edge, remove? All this is available. Okay, so these are the main methods of graph which should be available to implement. Now, the most important thing is you don't have any insertion logic or removal logic, because if it is an edge which has to be connected, so if you want to insert a vertex, you can directly go and insert it. And if you want to insert an edge also, the vertex destination is given, you insert it. So there is no checking you have to do, or there is no ordering you have to do, etc. So insertion removal is very simple. But how do you traverse through the graph is something very important. Graph traversal means visiting every vertex and edge exactly once in a well-defined order. So you track which vertices have been visited, which vertices have not been visited. So that is what is very important in a traversal. And that we will discuss two important travel methods. One is the breadth first search, and another is the depth first search. So these are the two important ways we will discuss how to traverse a particular graph. Okay. So now let's take breadth first traversal. This is one of the most commonly used approach. You start from a particular selected node, which is your source node, and you traverse the graph layer wise, exploring the neighbor nodes, which are directly connected to the source node, and then you go to the next level. So as the name suggests, you traverse the graph breadth-wise. First, you move horizontally, visit all the nodes which are connected directly. Then you move to the next layer. That's what you do in a breadth-first search. So usually, queues are used in breadth-first search because you will go one layer by layer. Nodes visited are marked as visited. Nodes which are already visited, you don't revisit again. So you mostly use a queue for a depth first search. Because every path you go for path with length 1, then you go for path with length 2, then you go for path with length 3. That's how you go. Okay. I will, instead of going to the algorithm, I will show you an example and come back to the algorithm. Then only you will understand it better. Okay. So this is the node. Okay. So we start with A. A is our source. Okay. Now, what are the nodes which are directly connected to A? That is what we will visit first. Okay. So we will maintain an order in which we are visiting. So L0, layer 0 is A. This is our first level. So we have L1 is all the nodes which can directly reach from A in one hop, one step. Okay. So from A, I can visit B. So I visit B. I mark B as visited. Okay. And the node, the edge through I visited, no, the edge through I visited, that I mark it as a discovery edge. Okay, discovery edge means I traveled through that to visit that B. From A to reach B, I traveled through this edge. To discover B, I traveled through this edge. So it is called as a discovery edge. Okay, then from A directly I can go to C, right? So this becomes a discovery edge and C becomes a visited node. Then directly from A, I can go to D. So D becomes a visited node and this becomes a discovery edge. Okay. Now, if you see, we have 3 discovery edges, 1 unexplored. These are all unexplored. We have not visited them. I will come to cross edge shortly. So now, are there any more nodes in L1? No. Are there any nodes which I can reach from just one hop from level 0? No. So we go from level 0 to level 1 nodes. We complete all nodes in one hop. Then we go to nodes with 2 hops. And then we go to nodes with 3 hops. So first we have to complete all levels with level 1, all nodes which are level 1. Then only we should go to E. From B, you shouldn't go to E before completing C and D in breadth first. So we have completed this, right? Now, since we have completed this, now we go to other nodes, right? So now we take B, right? So we done from A, we went to B, C, and D. Now A is completed. There are no nodes which you can reach from one hop from A. So you take B. Okay, you take now level 1, you take B, the next node, and you see which are the new nodes you can reach. Okay, so there is C, but C is already a visited node. So if you discover a path from one node to another node, which is already a discovery edge, that is, which is already visited. Okay, from A, you have reached to C already. So this is visited. Since this is visited, this particular path from B to C becomes a cross edge. Okay, so you already have a shortest path from A to C, or you already have a direct path from A to C. So this B to C path from the source will become a cross edge. But for B to E, it's a new unexplored node. So this becomes level 2 and this becomes a discovery edge. So now B is done. A is done. There are no more nodes which you can reach from B and A. Now you take C. Okay. So from C, you see whether you can reach any of the new nodes. You can reach D, which is already a visited node. So this becomes a cross edge. You can reach E, which is already a visited node. So this also becomes a cross edge. Now you see new node F, which you can reach through C. So this becomes a discovery edge. So F is visited from C. Okay. So A we have completed, B we have completed, C also we have completed. Now go to D. From D you explore if there are any new nodes you can reach out. No, I can reach out to F, but it is already a visited node. So this becomes a cross edge. There are no other new nodes which I can visit. So I leave out. Then I go to E. I see if there are any new nodes which I can visit from E. There is no. I see if there are any nodes which are unexplored yet or any edge which is unexplored yet. I will repeat the algorithm, but since everything is visited, we stop the breadth first search. Okay. So if you look for this particular graph from A, you can go to B. From B, you can go to E, A to C, to F, and A to D. So this is the main connected path, the breadth first search path. Okay. You have traversing through all this is the breadth first way you can reach all the vertices and all the and all the vertices. You can traverse through all the vertices. These are labeled as discovery edges. All the additional edges whichever are present are named as cross edges. Okay. Now let's go back to the method. So we will use Q here. So let's start BFS of G comma S. S is the source node and Q is empty. Let's take, we'll have a Q which is empty Q. Okay, first we will add the node. Say let's in our case we added A. Okay, and mark this as visited. So we will have A, B, C, D, E and F. We'll mark this as visited. A is visited. Now, while Q is not empty, remove a vertex from the Q whose neighbor will be visited now. So remove the Q. We have only one node. So you remove A. You process all the neighbors of this Q, V, whatever we got. So now V is equal to A. So process all neighbors of W, all neighbors W of V in the graph. If W is not visited, you NQ it and mark W as visited. Okay. So who are the neighbors of A? B. So I NQ B, then C, NQ C, and D. So I mark them as visited. Okay, this I complete. Now I have to repeat. While Q is not empty, I have to keep repeating these steps, right? So now I remove the next node B. So I take B and C, process all the neighbors of B, right? So I see C and C is already visited. So I will skip that. I will not NQ it again. Then I go to E, which is a neighbor. So I NQ it. And I mark this as also visited. Now I come back. I remove the next neighbor. Now V is equal to C here. So I see any node which is not visited. I see F. So I add this. E and D are visited. So I don't add them to the queue. Complete C. Now take D, all the nodes are visited, so I don't add. So this is removed, this is removed. I take E, all the nodes are visited. So this entire algorithm is completed. So the breadth first traversal, what it does, it visits all the vertices, determines whether G is connected, computes the connected components of G, computes the spanning forest of G. So all these things can be done by the BFS traversal. Okay. So with n vertices and m edges, the time BFS takes is n plus m. Why n plus m? Because it goes through all the vertices once and all the edges once. So that is why the total time is n plus m. This algorithm can be further used to find out whether there is a cycle, whether there is the minimum number of edges between two vertices, all that it can be used to find out. I'll explain the algorithm in a little more detailed way. This is the exact algorithm. So it's a recursive algorithm. Okay. So what happens first? You take all the vertices in the graph G and label them as unexplored. Okay, this is initialization steps. And you set all edges as also unexplored. Okay. And if there is a vertex with unexplored, you call BFS G of V. So that we start with the source vertex, BFS of G comma V. We start with the source vertex. So L0 is empty first. Okay. You insert the source vertex. So this is A. And the label of A becomes visited. So A becomes a visited node. Now, while L is not empty, you create a new empty sequence L1. Okay, L1 next level we are creating. For all vertices in the list, that is in this L0 list, You take all the edges which are connected, you get the opposite of that edge. So from A, you have one edge. So this, for this edge, the opposite will be B. For this edge, the opposite will be C. So you get the opposite W. Okay. And you see whether that node is explored or unexplored. If it is unexplored, you set that edge as a discovery edge. So in this case, B is an unexplored node. So you set this edge as a discovery edge. Okay, you label that as a discovery edge. You set the label of W to be visited and you insert W to the level 1. So you insert B here. Okay. If this is an unexplored node, you make it a discovery edge and mark visited. If it is an already explored node, you make it a cross edge. Okay. So you do this. So now A you did, right? And B also you will, C also you will insert here, D is also insert here. All will be based on these steps. Now you have completed all the incident edges of V, right? Now you go back. So this I is equal to becomes I plus 1. Okay, so this is done, right? For all elements you have completed in this L0 list. So you go to L1 list. Now in L1 list, you take first element B. You look at all incident edges of B. So what are the all incident edges of B? You have 1 edge, 2 edge, 3 edge, right? So you look at all incident edges of B. So you see whether the label is opposite. What are the opposite of? So if the opposite of is unexplored, okay, you can set it. But here there is nothing as unexplored. Okay, right? This node is unexplored. You get the opposite of it. If the node is already explored, right? You set the label as, if W is unexplored, you set the label as discovery. But here for C, if you take for C, if you take, it is already explored. So you set the label as cross. So this particular edge will be set as cross. But for E, the node is unexplored. So you insert a new sequence, right? So in that you insert E and you go back, set that as a discovery edge. Now you repeat that for C. From C, you again see a new node F. So you insert that in this sequence. Okay. And you add this as an explore and you repeat it. So all the other edges will be set as cross edges. So you have L2, 2 nodes E and F, L1, B, C, and D. This is the depth first search algorithm. Any questions in this?
No, ma'am.
Okay. So each vertex is labeled twice. Once as unexplored, once as visited. Each edge is labeled twice, once as unexplored, once as discovery edge or a cross edge. So setting the label takes order of 1 time. Each vertex is inserted into a sequence once, and you check method incident edges is called once for each vertices, right? So you explore each of the vertices once, you explore each of the edges once. So the total time is number of vertices plus number of edges to find out to traverse through the entire BFS. Okay. So, but the BFS representation should be an adjacency list structure. So the total degree is twice the M. So where you can use BFS to compute the connected components, to find a cycle, to find a spanning forest. If you want to find, given two vertices of G, do you want to find a path between the minimum path, the shortest path, or there is no path exists, then you can use BFS. Okay. Next, we will look at depth first search algorithm. So depth first search is a recursive algorithm. It uses stack. Here we use the concept of backtracking, that you are moving forward from one node until you reach the end, and then you come back and you move backwards on the same path to find the other possible nodes. Okay. All the nodes visited in the current path till all the you will keep backtracking until you have traversed all the nodes, etc. Okay, so we will use stack here. And you have to keep track of nodes which are visited or not visited. Okay. So in depth first search, what you do, I'll go to the example directly, and then we'll come back to the algorithm like previous time. So I start with A. I start with an unexplored node. Okay. And I go to the next node. If it is unexplored, I make it a discovery edge and I mark that node as visited. From that, I go to the next unexplored node. So I mark this as discovery edge and this as explored. So from this, again, I go to the next explored node. So here from C, I can go to A, but A is already visited. So I make this as a cross edge or back. Here we call it as a back edge because it is backtracking. And then from C, I go to D or E. So I go to D, I make this as a discovery edge. So I see whether any other options are there. No, I can go to A, but it is already visited. So this becomes a back edge. Then I come back to C. Then I see are there other nodes which I can go. So I go to E. And this becomes a back edge. Okay, so I don't complete all nodes of A and then go to B. That is, I complete one level and then I go to next level. Like that I don't do in a DFS algorithm. So I just travels through the depth and then backtrack. So in the algorithm, if you see, so traversal can be used to check whether G is connected, compute the connected components, etc. Again, this also runs order of n+1, right, to find a cycle, etc. So first you initialize all nodes unexplored, all labels as unexplored. Okay, and you start with the source vertex, you call DFS of G. Now this DFS of G, what it will do, that particular node like A, it will be set as visited. Okay. Now for one edge, okay, for all the edges, it takes one edge, it finds W. Okay. So now it finds W, here W is B. Now for that B, it sets B as visited. Okay. And this makes this as a discovery node, discovery edge, and now calls DFS of B. So what happens? DFS of B again will call this particular one. So again from B, you will check what are the connected edges. If it is unexplored, you find the W of it. If it is explored, what you do? If it is unexplored, you find the opposite. If it is explored, you set the label as back. So that is what you are doing. Here you come to B and you see what is the node, you go to C. Right? If there are nodes which are already connecting to, if there is an unexplored edge, you make it as a cross edge, sorry, back edge. So you call DFS of B. So from DFS of B, you see W, now W is equal to C. So you make C has visited. You set the edge as discovery. Now you call DFS of C. Okay. Now from DFS of C, you see what are the options you can reach. So you you'll see already there is an unexplored path. So unexplored edge. So you explore that edge, but the opposite is already an unexplored. It is not an unexplored node. It is already an explored node. So you mark that edge as a back edge. Then you go to the next edge. So you go to the next edge, which is D. So it is unexplored. So you add D here. So you call DFS of D. Now you go DFS of D. The only node it can reach is A. It is already explored. So you set the label as back. And now you return back to DFS of C. Now when you return to DFS of C, you will be in this step, right? You have, if you have done only one incident edges. So other incident edges, you will see what is unexplored. So this edge is unexplored, right? At this point of time. So you will see what is the other edge which is unexplored. Can it lead to a newer node? So now you call DFS of E. So it will be like this. DFS of A will call DFS of B. DFS of B calls DFS of C. DFS of C will call DFS of D as well as DFS of E. Okay, now this returns back to C. C has completed everything, returns back to B. B has completed everything, it will return back to A. So it's a recursive method. That's how it is completed. So DFS visits all the vertices and edges. The discovery edges are labeled from that you can find the connected components. All the other edges are back edges. Here also every vertex is labeled twice, every edge is labeled twice, and you visit once for every vertex. So the total time taken will be order of n plus m in case of a DFS also. Okay. So both take n plus m only, vertex plus edges. But in depth first search, it goes till the end, backtracks, see the others. That's how it does. In breadth first search, it completes each level. First level complete, second level complete, third level complete. That is how it completes in each level in a breadth first search. So comparing the applications, you can use DFS both for detecting cycles, connected paths, etc. For shorter path, BFS is more preferred. For checking whether two components are connected, then DFS is preferred. So the edge difference is here we have back edge in DFS. Okay. There we have a cross edge. Cross edge is the same level as the B or in the next level. Back edge will be in the previous level. So that is why it is called as a back edge. Here it is called as a cross edge. By repeatedly traversing with DFS, and we can easily test whether a G is a strongly connected graph. If for every DFS you visit from each vertex and you are able to traverse through the entire list, then you say that the graph is well connected. That is, all nodes can reach to all nodes. Okay, the strong connectivity graph. Let me now show you a visualization. Okay. So let's say we have some graph here. Let's first do a breadth first search. Okay, so what is the source node we are selecting? Okay, and let's say go. So from source, it goes to 1. This is a discovery edge. Then it goes to 2. Then from 1, it goes to 3. And then from 2, it doesn't have any new node, so it goes to 3. So you can see from source, this is level 0. Level 1 is 1 and 2. Level 2 is 3. Level 4 is 4. Okay. So you can see this is a cross edge because it is going to a path which is already available. Okay, the same we will do a depth first search. Okay, so it starts from 0, from 1 to it goes to 3, from 3 it goes to 4, it comes back to 3, 1, and from 1 it goes. Okay. So this is how it goes. Okay, let me create an input graph. Okay, let's do a breadth first search. Let's take 0 as the starting node. So level 0 is 1 and 2 level 1. So from 1 it goes to again 2 and 3. From 2 it goes to 5, right? So you can traverse only to 1, 2, 3, and 5. So these nodes remain unvisited, which will show that it is a not a fully connected graph. So there are two connected components in this. The same if you do a depth first search. One, two, it goes to two. From two to two, it goes to three. Three to four, it goes. Then it comes back to three and two, and then it goes to five. Okay. There is something called as topological sort where it visits each neighbor. So it is similar to that. In a DFS way, it finishes off that level. It checks for all the connectivity. These are all extensions of DFS and BFS. Okay. Other algorithms we will not go. That's not for the scope of this course. Okay. So we will not go into those other algorithms. There is one more example we can use. This is another one. You can see, say, let's say the start vertex is 0. Let's say if we run DFS, it shows the step-by-step process. So I will say from 1 run DFS. So from 1 to 2, 2 to 6, 5. Then from 6 to 7. Okay. So you can also see adjacency matrix representation, adjacency list representation. And this is the logical representation. Okay, let's take an undirected graph. Okay, let's do a 0. Okay. So any questions? Vignesh, Sri Vignesh.
Ma'am, I need to once again go through these topics.
Okay. Okay, we will see in the next class then. So
Ma'am,
yeah, yes.
ma'am, have you that? Uh, so I submitted the assessment one. I reached out to you.
Hmm.
So
Is
again,
it evaluated?
the person who evaluated that, he keeps on reevaluating. I shared the assessment file with him, PDF format only. 2 times I shared. Still, it is not graded, ma'am.
Your file was not opening. Even for me, it didn't open. In the whatever file you have submitted in the portal, right?
Yes.
That was corrupted. It didn't open for us.
Okay, ma'am.
So
That
I asked that the manual submission, which was there in the assignment, to be taken into account.
mm,
So I think they have done that. So you're not able to see the grades for your assignment 1.
ma'am. Yesterday at 7:12 he graded. Yeah, feedback says reshare the file PDF format to email ID again.
For assignment 1 or 2, you're saying?
One. I shared the file 2 times, ma'am. Same email ID.
Just checking. Okay, you send this file to that email ID you sent.
Yes,
Oh,
yes, 2 times.
okay, you send it to, you share that email with me. I will ask him to. Okay. Because your file was not opening, that was the problem.
Ma'am, I also shared the file to your for you also, ma'am.
Fine.
On
Okay, I will ask them to evaluate.
last Monday, ma'am.
Okay, I will ask them to evaluate.
Ma'am, will mid marks will be appear this week?
Mid marks are not yet uploaded for you.
No, ma'am.
Did you write midsem or regular? Sorry, regular or makeup?
Regular.
It should have been uploaded. Why it is not uploaded? I will check with Arjun once. Tomorrow I
Okay.
will ask them to upload.
Okay,
Its
ma'am.
evaluation and all is completed long back.
Yeah, but yeah, it's still not updated.
Okay. Yeah, tomorrow I will ask them to do it. But if I forget, please send me an email. Okay.
Okay,
If
ma'am.
it is
Sure.
not available tomorrow, please remind me. I will
Okay,
ask
sure.
them to share it. Okay.
Okay,
Thanks.
sure. Thank you, ma'am.
Thank you.